All right, so first lecture of Gen Chem 2 for the semester. We're going to talk about kinetics, what it is, what it tells us, and then we're going to start studying some rate laws today. Okay, your calculator needs to have a natural log button. I think everyone in here has that option on your calculator, but just in case, make sure you've got the natural log button, and then make sure you've got the E button, Euler's number, okay? We're going to use both of those functions over the next couple of weeks, so make sure you've got that on your calculator. If you've got a standard Texas Instruments or standard Casio, you're going to have both of those buttons. If you're using the same calculator you had from last semester, 99.9% chance of having it. All right, so let's just use stoichiometry as a nice reference point, right? Last semester, we spent a lot of time talking about stoichiometry, a lot of time. Tells us how much we can make, right? It doesn't tell us anything about how long that's going to take, right? Stoichiometry says we'll make 22 grams, but stoichiometry doesn't tell me anything about how long it's going to take or how that reaction is going to work out. It just tells me, here's the quantity I begin with, here's the quantity I can end with. Right? And so kinetics looks at rates. That's what we're dealing with. When we're dealing with kinetics, we're looking at how long does this take? How long is this reaction going to go? Is it going to take a day? Is it going to take an hour? Is it going to take 6 centuries? What? How long is it going to take? So kinetics studies the process rate. How long is it going to take? Stoichiometry is great and very useful because I can figure out how much I'm going to make, but stoichiometry will not be able to predict how long that process could take. Right? That's what we're looking at in kinetics. Kinetics also gives us information on the mechanism. So the mechanism is how this reaction occurs. We're just going to kind of introduce the word mechanism today. Next week is when we're really going to look at mechanisms in greater depth. And by the way, just FYI, the notes are already posted for the entire semester too online. So if you want to go ahead and download those, bring that to class, just add to it so you don't have to write as much. That's all available to you now as well. All right, let's talk about some symbols, some terms and some symbols. Maybe you know these already, maybe you don't. When you see brackets around something, that means molar concentration. Remember, molar, capital M, stands for moles per liter, right? Capital M. I underline it to distinguish molarity from molality, right? Molality is moles per kilogram. Molarity is moles per liter. So when you see brackets around something, that means concentration of whatever's inside the brackets in moles per liter. So if I wrote brackets around O2, that would mean concentration in moles per liter of O2, okay? So if I told you, if you just saw this, O2 with brackets equals 2.5, what am I telling you there? I'm telling you that the concentration is 2.5 moles per liter. Okay, that's what those brackets mean. Brackets mean molar concentration of whatever's inside the brackets. We also saw this term last semester, but just a reminder, uppercase delta, okay, lowercase delta looks like an 8 that you didn't fully close, right? That means partial. Uppercase delta means change in. And who remembers, is change in final minus initial or initial minus final? It's always final minus initial, right? We did this last semester with delta H, all that good stuff. Final minus initial. We're going to do delta H some more this semester, but not until after spring break. And so if I wrote delta brackets O2, what would that mean? Putting both of those two terms together. That would mean change in the concentration, right? Final concentration minus initial concentration. So delta brackets means change in concentration. Okay, just introducing some vocab, introducing some symbolism that we'll be using. So far, so good? I lost anyone? All right. Now, when you see this little 0 next to it, that little 0 means initial, okay? Because if we're talking about change, we need to distinguish final from initial, right? So that little 0 means initial. So if we're looking at change, well, how will we tell final from initial? Initial's got the little 0 next to it. Okay, so that's what that refers to. The little 0 refers to initial. So if I wrote this, if I saw this on a problem, that's telling me the initial concentration of KBr is 5 moles per liter. Okay, that little 0 means initial. And then if there's no 0, we could assume that that's at some point later in time. All right, so let's talk about reaction rate. So what happens when I combine my two reactants, reactant A, reactant B, stir, 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 right? The reactants are going to disappear over time. That just makes sense, because where are the products coming from? Well, the products are coming from the reactants. So if the amount of product is going up, then the amount of reactant has to be going down, right? Reactants go away with time, products appear with time. The rate of the reaction can be measured by either, right? You could either measure how quickly is the product forming, or you could measure how quickly are the reactants disappearing, right? Either way, because the amount of reactants is going to go down, amount of product is going to go up. So I could measure either one. We're going to look at change in concentration of reactants. Okay, that's what we're going to be looking at. We're going to be looking at the change in concentration of reactants. But I mean, you could go the other direction if you so wanted. So kinetics, like I said, is a study of how fast our change from reactant to product is occurring, right? There's initial, all reactant, and then some time goes by, more time, more time, more time, more time. Right, notice I'm getting more product, I'm getting less reactant. And then at the end, let's just say at the end of that minute period, I've still got a couple reactant molecules in there, but I got a lot more product than obviously I had at the beginning. And so we're going to be looking at change in reactants concentration, but you could do it, you know, the other way if you wanted to. So reaction rate, change in concentration of reactant or product with time, right? These are obviously going to have a unit of time, because if I'm studying this in milliseconds or hours or centuries, right, there's going to be some unit of time involved as well, which means there's going to be, just like if you're measuring your speed driving in the car, right, it's kilometers per hour, right? There's a unit of time. It's miles per hour. It's not just miles. That'd be total distance. If we're looking at rate, you need a unit of time in there as well. All right. So we're taking the reactant here, and we're measuring its concentration at different times. This is a figure from the textbook, right? So initially, that was the initial concentration. 50 seconds in, 100 seconds, all the way up to 10,000 seconds. And the concentration all the way down to 0, or at least to a point where my meter couldn't measure accurately. Right? So we'll just round it to 0. And so we can look at the rate in this interval, right? And then the rate in this interval, and then the rate in this interval, and the rate in this interval. Right? We're looking at the intervals here. And the average, right, would be the change in concentration over the change in time. Right? Just like think about your, you know, driving down the road, right? You might be starting out slowly. Maybe you accelerate to pass somebody, and then you get back to speed limit. You know, your average speed would be that change distance over change in time. Okay. The average rate decreases as the reaction proceeds. Okay. So far, so good, right? We're not doing anything too crazy yet. And so what we're going to do here, if we plotted, this is time, this is concentration, right? Concentration's going down, and the rate is actually going down, right? And so what we're going to be doing in our calculations today, we're going to be using what's called the method of initial rates. Did any of you do this in high school, previous classes, method of initial rates? We're going to be figuring out the initial rate, the very, very fastest rate. Okay, because we can say, all right, if we know the rate at the beginning, when it's going to be the highest, we can figure out what the rate is at some other point in time. Okay, but let's figure out what it is at the very, very beginning, when it's got the highest likelihood of being the fastest that it could be. Okay, so we're gonna start at the very beginning, where I've got the most reactant possible. That means that it's got the highest probability of being the fastest point. Does this make sense? That's why we're calling it the method of initial rates. And then when we start getting into an integrated rate law, then we can figure out what the rate is at some point down the line. Right? So this is why we're using the initial rate, right? Because that's where it's going to be the fastest. That's where I've got the most reactant. Does this make sense? Everybody still good? Because I want you to understand conceptually what you're doing before we do the math. Because if you don't understand why you're doing the math, you're just doing it for the sake of doing it, right? I want to make sure everybody's cool with the reason behind that. Okay, so this kinetic stuff is going to be with us for a couple weeks. So just make sure that if this doesn't make sense, that we stop and get clarification, because it is going to be with us a while. That's one of the biggest differences between Chem 1 and Chem 2. Right? In Chem 1, we're doing a new topic every week. In Chem 2, we focus for a long period of time on kinetics, and a long period of time on equilibrium, and a long period of time on thermodynamics. Okay? So that's one of the biggest differences. I just want to point that out. Okay, so this is the same idea, just using different substances. 100% NO2. Now we're in the process of converting, and now we've got mostly products. Still got a couple of reactants there. So a rate law. This is what we're going to be writing today. It's called a rate law. We're using the method of initial rates to write a rate law. Rate law is going to be specific for every reaction. Okay, every reaction is going to have its own rate law. And we're going to use a K, lowercase k. Please, 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 write this a lowercase k. Okay, because when we do equilibrium, we'll be using uppercase K, which is the equilibrium constant, which is not the same thing as the rate constant. Okay, so I write mine in cursive because I'm just that scrupulous, I guess. I write mine as a lowercase k, right, in cursive. Because I'm just not articulate enough in my handwriting to distinguish lowercase k from uppercase k. So I write lowercase k and then uppercase k when we get to equilibrium. Okay? And we're going to have exponents as part of our rate law as well. So our rate law will include a rate constant, which will be unique to every reaction, and exponents are going to be part of every rate law we write too. So the rate constant is unique, and then the rate law and those exponents will be unique. And all of this is in the notes online as well. So if you don't want to write as much for Wednesday, you can download it, bring it with you. Okay, so let's do the generic rate law. And this is what we can use for any reaction, for any old reaction. Okay? Again, we're only looking at changing reactants. We could do it by changing products, but we're not going to. We're going to do it by changing reactants. So the generic format, rate is equal to K times the initial concentration of A to some exponent times the initial concentration of B to some exponent. This is the generic rate law. Now we need to figure out the specific rate law. That's what our mission is, to figure out the specific rate law. And that's where the method of initial rates is going to come in, and that will allow us to solve for X and Y, which are going to be exponents, some number, and then that will allow us to solve for the rate constant K. So again, why are the products not considered here? How come C and D are not part of this? Do C and D exist yet at the very beginning? No, they don't. And then we're not measuring the rate of formation of this, we're measuring the rate of disappearance of this. Okay. So this is the generic form. But this is not giving me any useful information. I don't know anything meaningful until I know the value of X or the value of Y, right? Because this doesn't tell me squat. I need to know the value of X and the value of Y to actually have a real rate law, right? This is just kind of the slot that we're going to put the numbers into. Okay? Does everybody understand the generic form, what the generic form looks like? Yes? Okay. So like I said, we're doing this at the very beginning, get the fastest rate before it slows down any. We can always figure out what the rate is later using using integrated rate laws. Now we have to use experimental data, right? We gotta, because think about it, it's change in concentration. Well, that means I need experimental data, right? I need to know what those concentrations are and what did they change to. So we're going to use experimental data. Okay, so here's the reaction that we're studying. Right back here, I just use A's and B's. Here's the reaction we're going to study. Okay, NH4+, plus NO2 minus N2 plus 2H2O. Now, if I were you just as a student, I might want to watch this one, and then I can pause the recording and turn it back on for you to write some stuff down, okay? Because I don't think you want to write down the big, long table that I'm going to show you here in a minute. Right? If this is my reaction, what does rate equal? Rate equals K times what? Well, A is now NH4 plus to some value X, right? Times this to some value Y, right? You can use A and B or P and Q or alpha and beta. I don't really care what you use as your exponent here. That's the generic rate law. How do I figure out X and Y? Well, to get X and Y, I need some real data. Okay, now we'll skip this right now. We'll come back. Do you guys know how to solve for an exponent in a variable? Is that something you already know how to do? Do I need to spend time doing that? Let's do it just to make sure. All right, if you've got an exponent in the variable and an exponent, right? 5 to the x is equal to 212. That's not something you can do just off the top of your head, right? If they said 5 to the x is equal to 25, okay, that's easy. 5 to the x is equal to 212, not so easy. Right, so what we do to get the exponent is we're going to take the natural log of both sides. And now we can rearrange this and use our log rules. So if we say ln of 5 to the x, ln of 5x equals ln of 212. Now we're just rearranging this using our log rules, which you don't really need to worry about as long as you understand the method, right? X is equal to the natural log of 212 divided by the natural log of 5. Okay, that's how you would solve for that x. So if it's x in an exponent that you can't readily just look at and figure out, you would need to use this method. You would take the natural log of whatever it's equal to and divide that by the natural log of whatever the base of the exponent is. Okay? This I'm just showing you the rearrangement from the algebra standpoint. What you end up doing is taking the natural log of this, dividing it by the natural log of this. Okay, I'm sorry if you already know how to do this and I just wasted 20 seconds, but rather spend the time to talk about it than assume we remember it. Okay, so if you ever are solving for an exponent where it's something that's not readily obvious, this is what you would do. Natural log of this divided by natural log of this. All right, let's not do more on this. Let's just talk to me. How would we do this? If 6 to the x is equal to 950, what do I do? Right, natural log of 950 divided by natural log of 6. So we're just rearranging the algebra here. So 3.83, okay? Now 99% of the time, your x, 6 to the x, is going to be set to something that you can realize, oh, okay, I know what that is. But sometimes you get something funky, and you need to do this method. Now, here's the last one that might throw a little bit of a loop at you. If any number, it doesn't matter what this number is, any number to the x is being equal to 1, what's the only number x could be? 0, right? Because anything to the 0th power is 1. Okay, so it doesn't matter what this number is, it can be 4 trillion. If it's any number to the x is equal to 1, the only answer that x could be is 0. Okay, so just keep that in mind too. Okay, math sidebar over. Let's go back to how we do method of initial rates. So I have to give you the data. This is all stuff I've already said. Let's look at the data, all right? So we've determined what our generic rate law is. That's the generic rate law. Now my mission is to solve for x. My mission is to solve for y. And then once I know x and y, I can solve for k. Okay, but you got to solve for x and y first. That's step 1. And you've got to be given this data. So in lab this week, you're going to collect this data. That's what you're going to do in lab, and then you're going to figure out your rate law. Okay? So we've got trial 1, trial 2, trial 3. Okay? We've got concentration of NH4 plus, concentration of NO2 minus, and then the rate. So let's solve for x first. So what we want to do, that's x goes with ammonium, right? So we want to pick a pair where NO2 minus stays the same and NH4 plus changes. Because we can't have one equation with two unknowns, right? That would be a train wreck. So we want one of them to cancel out, okay? So we pick a pair, okay? If I pick this pair, these two are not changing, these two are changing, all right? Does everyone see why we picked trials 2 and trial 3? Because we have to have one of them not change so that this over this is 1, right? So we want to have one pair not change, one substance not change, one substance does change, okay? Now, here's something that you can do, and this is completely up to you, whether you like decimals or whole numbers. You could say 3 over 2 or 2 over 3. It doesn't matter to me. If you like a whole number, right, 0.2 divided by 0.1 is going to give you a whole number, whereas 0.1 divided by 0.2 is going to give you a decimal. So it's just completely up to you. If you'd rather have a decimal, if you don't care either way, right? Everybody understand why we picked 2 and 3. So now we're going to plug this information into this, okay? So I did 3 over 2 just so that I get a whole number. So 0.2 goes in right here, 0.2 to the x, and 0.01 goes in right here, is equal to 0.01 to the y. And now plugging in the rate right there, right? Rate equals k, NH4 plus to the x, NO2 minus to the y, right? I'm just literally plugging this information into this. K I don't know yet, so it's just staying as k. And now I'm plugging in 2, okay? There's the initial rate, and then k I still don't know. This goes here, this goes here. Now again, you could have done it as 2 over 3 or 3 over 2, makes no difference. When you divide these two by each other, right, k cancels, 0.01 to the y cancels, and I divide this by this, 2 is equal to 2 to the x. What must x be? X is 1, right, because anything to the first is itself. So that's why we did the sidebar on how to solve for x in an exponent if it's not something that you could readily tell. Now, if you had done it as 2 over 3, it would have been 0.5 is equal to 0.5 to the x. It would have been the same thing. Okay? Does everyone see how we did this? Does this make sense? Yes? No? Maybe? What pair should we pick for for figuring out NO2 minus? What pair should we pick to solve for y? 1 and 2, right. Because we want ammonium to be the same so that when we divide them by each other, these two are the ones that go away. And then this is the one changing. Okay? So we're going to do the exact same thing again. We're going to plug in our values. All right? This goes in right here. 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 This time, just for fun, I did 1 over 2. Right? You could have done it as 2 over 1. Would that have made a difference? No, it wouldn't. And then the rate, don't forget to plug in the rate. Rate goes right here. Rate goes right here. K is a value I still don't know, so we just leave it as K. Now I divide. K goes away, and 0.1 to the x goes away. And it gives me 0.5 is equal to 0.5 to the y. Hey, it's nice and neat. So y must be 1 as well. Okay? So now I know the value of x, and I know the value of y. So there is my rate law. Now, if you have an exponent of 1, do you have to write it? No, you don't. Okay, if it makes you feel better just to put it there because you worked really hard to get that 1, you can put it there if you enjoy putting it there, but you don't have to. Okay, so if you don't put that, that's fine. All right, now what if something comes out to be 0? What if this had happened to be a 0? Well, that means that it's not part of the rate law, right? Because anything to the 0 with would just be 1. Okay, so you would make a modification if it comes out to be 0. So there's my rate law. Rate is equal to K times NH4 plus times concentration of NO2 minus. Now the last thing I need to do is solve for K. Okay, now students really get kind of marbled up on the units of K, and the reason for this is because K has to do with the exponents here. Okay, K comes from the exponents here. If this is a 2 and this is a 2, right? That's going to give K different units than if this is a 1 and this is a 1, this is a 1 and this is a 2, right? K's units are not always going to be the same, right? Moles per liter is always going to be moles per liter, right? Molarity is always going to be molarity. But the units of K directly come from the unit of the exponents here. So let's just take a second and go through where these units are going to come from. I'm just going to make a blank slide here so I give myself some writing room. All right. Because if I want the camera to capture it, I need to be in this box. All right, let's just pretend that my rate is equal to K, and let's just use A and B. A, B. And I want to know what's K. So to get K, you go to your data table, all right, and you pick any one of these trials, whichever one makes you happy, trial 1, trial 2, or trial 3, it doesn't matter, and then you just plug the values in and solve for K, okay? But the units of K are when things get funky, so I'm not going to spend, I think you can do the math, but I want to spend time on the units. Okay, so let's just pretend that this rate, I don't know, let's just pretend it's 0.05 is equal to K, and then let's pretend this is 2, and this is 3, just for fun. Okay, now this brackets means moles per liter, right? And then this comes from what the rate was in my table. The rate here is moles per liter second. Okay, so we need to carry that with me. So we would say 0.05 moles per liter second is equal to K. What's 2 times 3? That's 6. Okay, watch my units. Brackets is moles per liter, right? And so brackets times brackets is what? What's moles per liter times moles per liter? Oops. What would that be? Moles squared per liters squared. Does everyone see how we did that? Right? Because this is moles per liter, this is moles per liter. If this is 2 and this is 3, I'm just making these numbers up. This would be 6 moles squared per liter squared. Okay, is everyone with me on how I did that? Just making those numbers up. So how do I get K by itself? Divide both sides by this quantity, right? 6 moles squared per liter squared divided by 6 moles squared per liter squared. Okay, so that's going to give me K, right? 0.05 divided by 6, you can do that in your calculator, no big deal. Let's talk about this piece. When you divide fractions, what's that the same thing as? Multiplying by the inverse, right? So we're flip this and multiply. Does everyone see what we did? Okay. Now we just simplify. This one goes away, that exponent becomes 1. This goes away, that exponent becomes 1. So the units I have are liters per mole second. And then you do 0.05 divided by 6 as the number that goes right here. Okay, the units of K are the thing that gets students the most. And again, it's because of the exponents here and here. Right? If this one had been squared, this would be moles cubed per liter cubed, right? Because this would be moles squared, liter squared times moles per liter. That'd be moles cubed per liter cubed. That's going to be different. Okay, so that's the one thing that algebraically is no different than any other algebra you've done your entire life. But watching those units, that's something that we haven't had to deal with up to this point. So you just plug in the trial for any trial you want. Pick 1, 2, or 3. Plug it in. I just picked number 2 because it's 0.1 and 0.01. All right, so my units are liters per mole second. And that's how you do it. Does anyone need me to go back so you can see something? Because the next thing you're going to do is you're going to do one yourself. You ready? Ready for the challenge? No, it's the first day of classes. Okay, so we can plug K back in. Now, the last thing I need to do before I turn you loose on one, when I ask you what's the order of the reaction, the order of the reaction is obtained by adding together these superscripts. So if I said, what's the order of this reaction? It'd be 1 plus 1, so it'd be second order. Okay, that's what the reaction is. If I said, what's the order with respect to ammonium? It's whatever that exponent is for that particular substance. That was the slide I skipped over a few minutes ago because it didn't make sense to talk about it at that point. All right, so this would be first order with respect to NH4 plus first order with respect to NO2 minus, but overall, the order would be 2. Okay, you just add those exponents together. Okay, so that's what I just said. Overall orders, adding them together. Now, if you have a 0 order, I just said this a minute ago, if one of your exponents comes out to be 0, anything to the 0 is 1, so it drops out. Okay, so if you ever get an exponent of 0, it just drops out. All right, so here's one for you to try. I'll pause the recording. Here are the experimental data. This is the reaction that you're studying, and these are the data you collect. Now, in the previous problem, I had the rate on the end. Now the rate's at the beginning. Rate, concentrations, trials 1, 2, and 3. I'm going to pause the recording, and I'll give you a few minutes to do this. So let's take a look at the solution here. So we're looking at permanganate and oxalate here, right? We're looking at these two reactants forming these two products. We've measured some rates for some different intervals for different trials, and we're looking at concentrations, and we're going to figure out what's the rate law for this experiment based on method of initial rates. So there's the generic rate law. Look, this time I just use M and N just for fun, right? You can use any variable you want there. You can use happy face and heart, you know, have some fun with it, right? You have to find little ways to be excited in life, right? So we're going to solve for the real rate law, right? This is just the generic rate law. This is the dummy rate law, right? We need to solve for the actual value of M and N, and then we need to solve for K. Okay, so we want to pick a pair where permanganate is changing and oxalate is not. So I picked trials 1 and 2, right? There's the rate, there's concentration, there's concentration. Notice this is the one that's going to cancel. This is the one that's going to not cancel. Okay. So 1 over 2 or 2 over 1, it makes no difference. You can go either direction, whichever floats your boat. Okay, so notice what happens here. 0.05 divided by 0.05 is 1, right? And 0.5 divided by 0.75 is 0.67. So I get 1 is equal to 0.67 to the M. Well, it doesn't matter what this number is. If it's some number to an exponent being equal to 1, why is M 0? What's the only way that you can have some number to an exponent be equal to 1? If the exponent is 0, right? I remember when I was in high school, I was taking like Algebra 2, I think, and we were taking some sort of test on like reducing polynomials and stuff, and it was this big, nasty, complicated thing. And then it was to the 0th power, and we were supposed to write that value. And some student walks up, and some student walked up and goes, "Is this to the 0th power? I just don't know what to do." And the teacher goes, "Shh." And I'm like, "Ah, you just told the answer." Right? So anything to the 0th power is going to be 1. So now we're going to solve for N. So we're changing oxalate. We're leaving permanganate alone. So I picked trials 1 and 3, right, because we want this one to go away and this one to change. And so you could have done 1 over 2 or 2 over 1, right? If you're looking ahead and you're going, you know, I'd rather have a large number, then set it up one way. And if you're like, I don't care, then just plug and shove it, right? So 0.5 is equal to 0.5 to the N, because I used N this time, right? So anything to the first power is itself. So that's why N equals 1. Does everybody agree that the exponent for oxalate is 1? So Have I gone through this too quickly, first of all? Okay. So now, because this is 0 order, does it show up in my final answer? No, because anything to the 0th, whether it's some nasty algebra problem that you're reducing in 10th grade, or if it's just, rate, anything to the 0th is 1, so it goes away. So rate is equal to K times the concentration of oxalate to the first. So what's the order WRT stands for with respect to? What's the order with respect to permanganate? Well, we say that order is 0, right? It's 0 order. What's the order with respect to oxalate? First, right? And what's the overall order of the reaction? First, right? We still have to solve for K, though. How do we solve for K? We go back to the data, and then we pick any trial we want, right? Any trial that makes us happy. You can pick 1, 2, or 3. Now, the units here are going to be different this time, because in the previous problem, we were multiplying moles per liter times moles per liter, right? That gave us moles squared per liter squared that we then divided. Here, I just got moles per liter, so that's going to be different. And the units of rate are moles per liter second, so the unit of time here is second. We're measuring it in seconds. So I just picked number 1, plugged it in, and I got K, moles per liter divided by moles per liter, right? Those cancel out. That's why it's just seconds inverse. Do we agree on K? Now, please, please, please make sure you're denoting this as lowercase k, okay, because next K you will see is uppercase K, and that's very, very, very different. That's the equilibrium constant, okay? We're going to be dealing with lots of Ks this semester. I'm sorry. I'm just saying that now. I'm sorry. How do we feel about this? On Wednesday, we're doing enrichment, so I'm going to give you problems. You're going to work. You're going to collaborate. We're going to go over them. Okay, that's what we're going to do Wednesday. So if you're still feeling kind of fishy about this, don't be. We're going to work on it more on Wednesday. So that's where we'll stop today. Have a great first day back, and I'll see you Wednesday.